start. Wait. Okay, now I have trouble. Why didn't I see anything? Oh, because okay. Should be fine. Okay. So any question from this time? Let's go over a quick overview. So this time we start this concept of density matrix, and a very basic motivation of it is we want to describe a classical probability mixture of quantum states in some nice mathematical form. So first we have this equivalence between ensemble interpretation of whole bunch of quantum states and this density matrix. So ensemble is just what we said. It's a classical probability mixture of things, and here the things are quantum state. So you have this ensemble where you have a whole bunch of quantum states psi I, each is getting picked at probability pi, and then we can define this. Well, this is just a function here. So from this ensemble, you can calculate the density matrix, that is summation pi and the projector onto psi I. Right. And yeah, and we show that every feature of this ensemble can be just calculated from this density matrix. And also, this mapping from ensemble to density matrix is not one-to-one. There are many ensembles that will map to the same density matrix, as we'll see later. Okay. So here we have a derivation that this rho actually describes everything about the ensemble. And then we have this nice theorem says that a density matrix is more of a standalone object because you can just write down a matrix and check these two conditions. You check that it's well normalized, the trace is being 1, and your matrix is positive semi-definite PSD. If the matrix satisfies those two conditions, then it's a valid density matrix describing a quantum state, i.e. There is a corresponding ensemble. And also this is if only if it's easy to check that whenever you have an ensemble quantum state, then its corresponding density matrix satisfies those two conditions. So if you have those two conditions, then your density matrix is valid. And because of this theorem and everything we done, now we can rewrite all our postulates about quantum mechanics in terms of those density matrices. And we'll see today that so our starting motivation is density matrix is describing a classical probability mixture of quantum state, and we'll see today that you can also get those density matrix from considering a subsystem of a quantum system. And that means that if you have an open physical system, your system is interacting, your system here is interacting with another system, then your local part of your then this local part of your system can be described by a density matrix. But that's a little spoiler. Anyway, we can describe everything of a physical system in terms of density matrices. And density matrix is is a matrix that acts on some linear space. and it satisfies those two conditions we just talked about. It must be PSD and the trace need to equal to 1. And okay, so we talk about open system, then we back to closed system. And but if the system is no longer evolving, no longer interacting with other systems, then the evolution of your system is still described by a unitary matrix, and your density matrix gets mapped in this way when you apply a unitary on it. So rho become, I forgot to change this. Okay. Rho become rho prime, which is u rho u dagger. Okay. And we are going to see a whole bunch this kind of formula a lot. So rho will get changed to something that's some matrix rho and matrix dagger. And yeah. And the next example is exactly what we said. So measurement. If you apply a measurement described by the set of measurement operator n sub n, then your rho basically become this subnormalized matrix n sub m rho n sub m dagger. So this m rho m dagger when you have outcome small n happening. And from here you can calculate the probability. So probability is just the trace of this matrix here. And you can calculate the normalized state. So you normalize this state by dividing the probability. This is the collapse post-measurement state. And also here, now we know how to describe a probability mixture of things. We can describe this weird state as post-measurement state, but you cover up the outcome. Although when you do measurement, you should know outcome, but if you forgot your result or something, or someone know you are doing the measurement, and someone know you are doing what kind of measurement, but they don't learn the outcome, then your density matrix becomes this probability mixture of all the outcomes, and it's actually a nicer form. It is sum over all outcomes, then m rho m dagger. Okay. And once again, we have, if you have composite system, then your joint density matrix is the tensor product of everything. So rho 1 tensor rho 2 rho 1. And you can have entangled state. Any question? This is formulating quantum mechanics in terms of density matrices. And then we talk about the equivalence of different ensembles. So as we mentioned many times, different ensemble can give you the same density matrix. Here is a very famous example where in 1 qubit, if you have 50-50 mixture of any two orthogonal basis, any two orthogonal state, then it will become this totally mixed state. So in particular, z direction 50-50% and x direction 50-50% is actually the same state. It seems a little weird in terms of physics, but that is true. You can check all the measurement outcome has the same probability distribution. Okay, and now this is the very annoying theorem that will skim over the proof today. Yeah, I will just describe the main point, and you can check the details on lecture note or on the book. I think here I have more details than the book. So if you are very picky about the mathematical detail, you can check the lecture But anyway, here we are characterizing what kind of ensembles have the same density matrix. And they are associated, and the theorem says that they have the same density matrix if they are associated with some unitary in this way. So first we define the subnormalized state, kind of just like before. So you multiply your state with the square root of probability. So this thing no longer has known one, but you don't need to write the probability anymore. And so one example has a whole bunch of subnormalized state, and another example has a whole bunch of subnormalized state. And if they are related by a unitary in this way, so yeah, I'm not quite sure how to describe this, but it feels like these states are kind of a basis, and you can do a unitary transformation to another state. But mathematically, if every psi tilde can be written as summation j uij phi j tilde, then those two ensembles are describing the same density matrix, and this is if and only if. And for the proof of this, let's describe the annoying part first. Okay, so this is if and only if. So one of the direction is actually easy. So the if direction, if your two ensemble satisfy this relationship, then you can just do the calculation. You can just write the density matrix related to this ensemble and use this relationship. So the density matrix related to psi, and you use the equation given to write it as write it in terms of the phi tilde states. And then you use this U being unitary to show that this is actually a density matrix related to the phi state, phi ensemble. So this is easy, you just do the calculation. Now, the other direction is you have the density matrix of two ensembles are the same. So let's call this density matrix A, and you want to show that these two ensembles satisfy this kind of unitary relation. So you want to find a Cij here. You want to find a Uij here, and then show that it's elements of a unitary matrix. And it is very annoying because dimension of everything doesn't fit. So why do I say dimension? Because I say this kind of like a unitary matrix, but it's not quite a square matrix yet, because those psi and phi j, they can have different number of I and different number of j here. And also the number is different from the dimension of the Hilbert space. So it's hidden in a notation, but this I can be from 1 to 100, and j can be 1 to 200, and the dimension can be 2 or 5. And okay, so there are three numbers that are different, and well, when we think about unitary, we kind of want it to be a square matrix. That is okay, because we are just appending zeros if one number is smaller than a number. So let's say m is 200 and n is 100. Then we just add a whole bunch of dummy summation. So we change the summation from 1, we add 100 zero vectors. So you just have a whole bunch of projector onto some psi tilde that's actually 0. Okay, so that's how you fix the dimension doesn't fit. And we will do similar thing on the dimension of the Hilbert space. So the thing we want to do is, well, we know those two things are equal to some density matrix, and we diagonalize the density matrix. And so here are the eigenvalues and the eigenvectors of this density matrix A. We can do this because remember, density matrix is PSD, and PSD matrix are diagonalizable with positive real eigenvalues. Anyway, you diagonalize A, and you split up this lambda into square lambda, and write this in terms of k tilde and k tilde, so everything has a matching form. And the idea here now is we split up this relationship into two things. So we want to show there's one unitary that changes from those k tilde to psi tilde, and another unitary changes from this k tilde to phi tilde. Okay. And well, the sum k and the sum n here have different dimensions, so there are a whole bunch of padding 0 you need to do first. So you can see here that the first thing you need to deal with is some of the eigenvalue here might be 0, so this might not go to 4-dimensional Hilbert space. And you can just once again write some dummy vectors that has length 0, and in the end you find some Cik and and one dimension is n and one dimension is k, but you can also extend this to a 4-unitary. As a bonus question, you are homework sure. So this unitary satisfies the orthonormal condition for all its columns, and then you can extend it to the 4-unitary. Okay. And so that's all the padding zeros. And let's go back to one level. So let's see the high level thing we want to do. So this matrix from psi tilde equal to A, and the matrix from phi tilde was equal to A. And on a high level, then we will show this relationship. So the psi tilde can be written as some Cik of k tilde. And you show that the Cik is basically a unitary, although there is some, after you fixing the dimension issue, the Cik is a unitary because the columns satisfy this orthonormal relationship. And so you can really write this. Okay, so I rename this C, so I fill this C to a unitary and call that V. So those psi tilde is some Vik of k tilde. And similarly, you have phi tilde will equal to some Wjk of k tilde. This W is also a unitary. Then you can just piece things together, although we are missing some detail also, but you can just write your unitary U, the unitary we want to find as W times as V times W dagger, because if psi and k are related by unitary and ki and phi are related by unitary. Yeah. So here our idea is this psi is like x and k is like z here. So psi is like v times z and phi is like w times z. Then z equal to w dagger times y, and then x equal to v w dagger times z. And anyway, so dagger of a unitary is still a unitary, and two unitary multiplying together is still a unitary, so this u is a unitary. So that's a high level idea. You show that there is a unitary relating this a and phi tilde, and another unitary relating this this psi and this and this phi and a, and so there is a unitary relating this psi and phi. Okay, then finally let's check the calculation we need to check. So why is this Cij a unitary? Well, so we start from here. So first so those Cik are found by decomposing those psi tilde into the basis of k. Okay. So we try to find the coefficient of those psi tilde on the eigenbasis of A, and so let's forget about the zeros first. So first we project, so write identity as sum over projection onto the eigenvectors of A. So this is just using a completeness relationship of the eigenbasis of A. And then we move things around. So there's this k projection with psi tilde. So we leave it here, and we renormalize this k by dividing this square root lambda k, because we want to describe things in k tilde. And because we are doing, so you can see here that we are doing this dividing by square root lambda k. That's why we need to deal with lambda k being 0 carefully before. And yeah, you can check that these we have been dealt with. And anyway, so those lambda k are actually all non-zero, and this whole thing is defined as Cik. So the coefficient of psi tilde I on k and divided by square root lambda k is just Cik. And then we can use this relationship that those k and those psi tilde give the same matrix. Then those psi tilde, excuse me, yeah, and then we write all those psi tilde instead of those k tilde again with this relationship. Then we get some equation on those Cik and those Cik, and also CIL star, because there are two psi, so there are two indices. So the first one becomes Ci sum over k, Cik, and the second one we use the dummy variable L. Yeah. So sum L tilde, CIL phi. And anyway, we got this equation. And so some k tilde projector equal to some KL, and this is something that's a function of k at L because all I are summation over and k tilde L tilde. And here this is a little too wordy. Anyway, so we know that all those k tilde are orthogonal to each other, right? Or they are not normal, but they are orthogonal to each other. So you can probably easily see that if you want this thing to equal to this thing, and because this is a diagonal thing, then all those things should equal to delta KL, right? Because if you think this is kind of like a matrix, then these are all diagonal, so all the off-diagonal elements should be 0. That means this is like a delta function, and also on the when k equal to L, you want this thing to be 1. So this thing should be but we do something here, so we change L to J. But anyway, sum over I, Ci, K, Cij star should equal to delta Kj. If you want detail, you can check this. And yeah, but now as we said, then we think C as the matrix, so Cij. So we view this Cij as the ijth element of matrix C. Then this relationship just means that the k's column and the j's column are also normal to each other. And and because of that, you can extend C to a unitary, and then you can find another unitary W and finish the proof we said before. So, any question on the high-level sketch of this proof? We skip over all the annoying details of appending zeros. But, I don't know. Some comment from myself is I find this less intuitive than it should be, because it's a unitary that rotating a very weird dimension, because it kind of rotated on a fake dimension, because the dimension of those I and J, as I said, doesn't really has any physical meaning. It can be arbitrary large number, doesn't relate to your physical space, and it's a little hard to imagine rotation on that dimension, but you can always come back to the mathematical form, and this is what is true. Okay, then we have lots of time. We have 22 minutes left. We are very fast. We can probably have extra topic before midterm. Anyway, so let's go to the real motivation of density matrix. That is reduced density matrix. I guess I should not say real, more like more physical motivation. So density matrix is a very nice way to describe the subsystem of an entangled state, or just or just any state, but any state, then the substate is just a pure state, then you don't need a density matrix. But so the situation is you have system A and system B, or even, and A and B might be entangled. So then you have a global state with a global density matrix that's on this space HA tensor HB, and so this rho AB is actually maybe it's like psi AB. Say the total state, we can consider it as Okay, so this rho AB is maybe psi AB, psi AB. Okay? So some entangled pure state over the whole system. And then we want to describe what Alice can see on her own part. Then we will show kind of that this can be described by this reduced density matrix rho A. So it's a density matrix on A's part. And this reduced density matrix is calculated by doing this partial trace operation on the global state rho AB. Okay. So for the rest of today's class, we are going to talk about this partial trace. It's an easy calculation, but it's a quite an important concept. So what's this partial trace operation? Well, first is operation that map a bigger matrix to a smaller matrix. So actually, okay, so here here I make a little mistake. Okay, so those HA and HB are space for vectors. So and we don't have. Okay, let's be very picky. So let's be a little careful here. So those should actually be operators on HA and HB, right? So L of HA tensor L of HB. Let's just be very picky. So those are matrices that map from HA to HA, and the matrices that map from HB to HB. And here we should have L of HA tensor L of HB map to L of HA. Okay, so a small direct equation. But anyway, partial trace will map a density matrix that is on this bigger system A and B to a density matrix that's just on system A. And here is the definition. So we use this a little lazy way to define things. So we defined it on all computational basis state. So if you have so computational basis for matrix, and that's just every matrix element. So it's a matrix that's the ijth element on HA on A part, and the KL's element on the B part. And if you do partial trace, then the A part preserved is still ij, and the B part becomes this number of delta KL, which is right here, which is the trace of KL. Yeah. And so that's just how this operator do on basis element, and we extend this to everything by also saying that this trace, partial trace, is bilinear. So if you have a density matrix that's A rho 1 plus B rho 2 on the A part, then the result of doing partial trace is this linear thing. So it's A of partial trace rho 1 tensor sigma, and the partial trace rho 2 tensor sigma plus B. And also it's linear on the B part. So if the B part is A sigma 1 plus B sigma 2, then you have this A partial trace B plus B partial trace B. Okay. And just from those three relationships, you can see that partial trace of everything is defined, because you can decompose any density matrix as summation of those basis elements, and just use this bilinear relationship to expand out everything. And okay, so that's a very axiomatic definition, and we can see some example. So let's say something more complicated, but still quite pure. So you partial trace some state as A bar, A cat A bar, tensor B cat B bar. Then here we see that it's really like a trace. Then you are equal to, you preserve the A part and just trace the B part. Okay, so this thing, yeah, sorry. So yeah, you preserve the A part and trace the B part, and because cyclic relationship of the trace, then the trace B part is just B2 bra and times B1, and this is inner product between B2 and B1. Okay. And once again, important thing to remember is that partial trace map a bigger matrix to a smaller matrix. So here, remember this A1 bra A2. This A1 bra A2 is the matrix matrix on system A, or LOFHA, and B2 inner product is B1. This is just a number. Okay, so the dimension on B part just disappear, it become a number. Okay. And also the definition we have here is a little more general than just mapping a density matrix to a density matrix. You can see that we didn't require anything here to be density matrix. It can be any matrix, and we can define this partial trace. Okay. And then we can also have more general state. Yeah, a little more general state than this. So if we actually have two density matrices, and let's say our density matrix has this nice form that rho AB equal to rho A tensor sigma B, then yeah, then this is also something you can check back home. Do we have? Probably don't have homework. Maybe we can have homework. Let's write it here. And anyway, if you do partial trace B here, then you see that what happened is you get rid of this tensor and you just trace the B part. Okay. And but now here we say everything is normalized. Okay. And so everything is normalized, and this sigma is actually a density matrix. So that means this trace sigma is 1. So the rho A here, when your system is just rho A tensor sigma B, is rho A. And that's nice. That's what you expected, because this rho A tensor sigma B is just system A and system B, not just staying there and not interacting with each other. And you expect that if your system A is not doing anything with system B, then whatever state on system A is a state on system A. Okay? So this is like a sanity check of this partial trace operation, that you actually describe the system when describing the subsystem when we don't have any interaction. So that's nice. And then here we also have another notation, so product state. Wait, do we? Oh, we probably haven't, but anyway. So this is product state for density matrix, just means whatever state that can be written in this form. Okay, so basically no entanglement state, no entanglement. If a density matrix can be written as one density matrix, tensor product with another density matrix, then it's a product state, and it means it's not entangled state. And it's a little confusing, but product state and the pure state are different things. Pure state means a state that's not mixed. So let's see an example of a confusion here. So this is a pure state, but it's not a product state. Okay? So our favorite entangled state, the maximally entangled pair beta 0, 0, that's 1 over square root 2, 0, 0 plus 1, 1. And you can try to prove that this is a entangled state, so it's not a product state. When you write its density matrix, you write out the element is this form. It should be B cat, B bra, and you just multiply all everything, then you got these 4 terms. And you can kind of see that why we don't want to describe everything in terms of density matrix, because here this beta 0, 0, you only have 2 terms here, but when you write it in terms of density matrix, there are 4 terms here. So in general, if you want to write a pure state in terms of density matrix, there is this n squared blow up, and it's very annoying to just write down. So when you do calculation, when it's a pure state, you wish to make the calculation stay in pure state. Anyway, so let's go back to one level point. So this is an entangled state, but it is a pure state, right? In terms of this total, this rho AB whole state, it is a pure state. It's just projected onto this beta 0, 0. Okay. So let's write this down. It's entangled pure. Okay, now there is a more confusing part. Now we want to calculate the reduced density matrix of this row. So this is row AB. So let's say this is row AB and this is row A. It's easier, AB is easier than 1, 2. Okay. And we trace B. Anyway, so let's see the partial trace operation. And so let's write down everything first. So trace B of this whole thing, and we already use this being bilinear. So this 1/2, because this is linear, then you can pull it out, and you have those 4 things. And you do, well, here we can just use the definition here, right? We use the definition here. Those states are all in computational basis, and then you see that only thing survive is this 0, 0 and this 1, 1 thing, because the inner product of the second part, this thing 0 and 1 inner product, 1, 0 inner product get cancelled out. So only thing survive is this 0, 0 and this 1, 1. And it's a totally mixed state. That we said before. It's 1/2 projected onto 0 and 1/2 projected onto 1. It's a totally mixed state. And then a little confusing part is here is that the global state is a pure state, but the reduced density matrix is a mixed state. Okay, and I'm not sure we have a theorem here. but maybe. But another thing that's also true is that, so if your global state is pure and entangled, then your reduced density matrix is always going to be a mixed state. But if your global state is pure and also not entangled, then your local state is also going to be pure. And you can kind of see the non-entangled to non-entangled thing, because non-entangled pure, then that means both this rho and sigma is going to be pure. Then you reduce it and it's still pure. And another thing that's also true is that's a if only if thing. So if you have pure and entangled, then you trace out a part, then this entangled makes the local part mixed. Do we have time? I guess first, any question? What's this partial trace operation? This is an important operation that you should really understand, and it will be your homework, and it will be in your midterm. So, and the most basic way to calculate it is doing things like this. You can write down everything in terms of basis element, and doing the partial trace one by one, or those two examples are also how you can use. So you can remember that if your state has this form, then you can do partial trace on this part. Or if you have this, you can write the state as two density matrix, then you can, this might not even be matrix, might not even be density matrix. So if your state can be written as tensor product of two matrix, then you can write it as this. And if trace rho also equal to 1, then it's this. Okay, and we have 3 minutes. So we probably don't have the time to prove this, but but we can have a really brief description. So reduced density matrix, we want to say it describe everything about a subsystem. So so the first thing we want to check is that the reduced density matrix describe every measurement outcome of your subsystem. So once again, the setting is like you have system A and system B, and they have a global, maybe entangled state. And they want to say we then separate these A and B far apart, and we want to do some kind of measurement on A. And we want to say the reduced matrix on A, so on row A here, will describe every part, all the measurement outcome distribution on this system. And here we give a very sketchy proof. You use some physical principle. So we say, because A and B are entangled state, and entanglement actually don't care about physical distance. So you can prepare A and B entangled and separate them really far apart, maybe separated by 100 light years away, right? And then because they are really far apart, you do any measurement on B that doesn't affect things on A, because there is no signal principle. It's 100 light year. Anything you do here require 100 years to affect anything here. So you can just measure your system B in computational basis, and that will collapse your system A into some state. And that state should, the collapse state should have same measurement outcome as if you don't do any measurement on system B. And if you calculate that collapse state on system A, and that will be your reduced sense matrix partial trace B row AB. Okay, we are a little over time. Any question? Otherwise, that's for today. Good? Okay, then see you on Thursday.